Good day. We'll continue our lectures on application of complex numbers to series AC circuits. So here we'll be dealing with how we can apply the complex number that we have done in the last lecture on AC circuits, but we are going to be limiting it to series circuits. As you know, complex numbers are very useful in AC circuit analysis. And why is that so? We are going to learn it in this course. So at the end of this unit, you should be able to appreciate the use of complex numbers in AC circuit, to be able to perform calculations on series AC circuit using complex numbers. As I've said in the past, complex numbers are useful for AC circuit analysis because they provide a convenient method of symbolically denoting phase shift between AC quantities like voltage and current. When analyzing AC circuits, it is found that quantities of voltage, current, and even resistance, in which case, when it's AC circuit, we call it impedance, they are not the familiar dimensional quantities used in DC circuits. So rather, these quantities, because they are dynamic, they are alternating in direction and amplitude and possess other dimensions that must be kept into account. Therefore, frequency and phase shift are two of these dimensions. The frequency changes because of the waveform. Even with relatively simple AC circuits, dealing with a single frequency, there is still phase shift to contend with in the addition of amplitude. So a complex number, as we have said in the last lecture, is a single mathematical quantity able to express these two dimensions, that is the amplitude and the phase shift at the same time. So oscillating current and voltage, these are complex values that have a real part, and we can measure an imaginary part which we cannot measure. I told you the last class, for a complex number, there's an imaginary part and there's a real part. So also AC circuits, where we want to do the analysis. So simple AC circuits may be analyzed by using phasor diagrams. However, when circuits become more complicated, analysis is considered and simplified by using complex numbers. So we are going to start with the series AC circuit. Series AC circuit. So in an AC circuit containing resistance only, you can see that in figure A here. What usually happens is that the current IR is in phase with the applied voltage. We have learned that in the first class of this module. So, and this is shown in the diagram of figure B. So the phasor diagram may be superimposed on the Higram diagram as shown in figure C. So the impedance, which is Z of the circuit, is given as VR at an angle of 0 divided by IR at an angle of 0, which is the same thing as resistance. Same thing as resistance. So let's move on. In a purely inductive circuit, we know that it contains a pure inductor, that is, no resistance is attached to it. That's our assumption, as you can see in figure 2A. So the current lags the applied voltage by an angle of 90 degrees, as shown in the phasor diagram of figure 2B. So the phasor diagram will be superimposed on the Higram diagram as shown in figure 2C. So the impedance of the circuit will now be given as Z equal to VL at an angle of 90 divided by RL at an angle of 0. So at the end of the day, it will be VL over IL at an angle of 90 degrees. So I will know that VL over IL is XL. So what we get is XL at an angle of 90 degrees. And we can say is JXL. JXL. That angle 90 degrees is denoted as JXL. So where XL is the inductive reactance, which is given by what? Which is given by 2 pi FL or omega L. That is XL. It's got omega L or 2 pi FL. So let's see purely capacitive circuits. In an AC circuit containing pure capacitance, only the current IC leads the applied voltage by 90 degrees as shown in the phasor diagram of figure 3b. So the phasor diagram may be superimposed on the Argand diagram as shown in figure 3c. So the impedance Z of the circuit is given as Z is equal to VC at an angle of minus 90 because it is lagging, divided by IC at an angle of 0. So at the end of the day, you are going to have XL at an angle of minus 90, and that minus 90 degrees minus J. So we can say minus JXC. So where XC is what? Is the capacitive reactance given by XC is equal to 1 over omega C, which is equal to 1 over 2 pi FC. So where C is the capacitance in farad. So if you look at the analysis, I have told you how you can, when you divide, how you can get the conjugate. So when you do the analysis, you get 1 over J omega C. So that is that about that. So we want to look at the series RL series circuit. RL series circuit. So if you look at the diagram, the circuit contains a resistance and inductance L in series. This diagram 4A, that's what it contains. You can see it. So the applied voltage V is the phasor sum of VR and VL as shown in figure B. So the current I lags the applied voltage V by an angle lying between 0 and 90 degrees. So it lies between 0 and 90 degrees. So the actual value, depending on the values of the VR and VL, it will depend on the values that we have for the resistance and the inductance. So the circuit phase angle, that is the angle between the current and the applied voltage, is shown as angle phi in the phasor diagram. Angle phi in the phasor diagram. So, and in any series circuit, the current is common to all components. That is, you take it as a reference frame, and it's just taken as a reference frame. So the phasor diagram may be superimposed on the Argand diagram as shown in figure C, 4C, where it may be seen that the complex form of the supply voltage V is given as V is equal to VR plus JVL plus JVL. And so that's what you have here. So now, the complex form of the impedance, it will be given by, sorry, this is not correct. This V is supposed to be Z. So Z is equal to R plus JXL. Z is equal to R plus JXL. So let's do something. So this is Z. This is Z. So Z is equal to R plus JXL. So let's go for that. See. Yeah. So what is the implication of what we have just done? So the implication is that, for example, if you have an impedance that is 3 plus J4 for the RS circuit that we have just done, it means that the resistance is 3 ohms, while the inductive reactance XL is 4 ohms. So you can also write it in polar form. In polar form, your Z is what? Z at an angle of phi. So where from the impedance triangle that we have done in the past, the modulus of the impedance Z is what? Square root of R squared plus XL squared. So that's where you can find the angle from. And so the circuit phase angle phi is arctan XL over R, and it will be lagging. So it may be for RC circuit now, since we have considered RL, let's see RC series circuit. In an AC circuit containing resistance R and capacitance C in series, as shown in this figure A, you can see that the applied voltage V is the phasor sum of VR and VC, as shown in the phasor diagram, this phasor diagram 6B. So what happens is that the current leads the applied voltage V by an angle which lies between 0 and 90 degrees. So the actual value of this will depend on the values of our VR and VC, and which also depends on the value of the resistance and the capacitance that is given to us. So the circuit phase angle is shown as angle phi and in the phasor diagram. So the phasor diagram may be superimposed on the Argand diagram as shown in figure 6C. This C. So, and what happens is that it may be seen that the complex form of the voltage will be given as V is equal to VR plus JVC. This is C. Sorry about that. JVC. This is C. JVC as JVC. So, and if you look at okay, let's move on to the next slide. Let's move on to the next slide. Okay, good. So, and also we can see that from this diagram, we may be able to see that the complex form for the impedance Z, impedance Z is, this should be Z, impedance Z is given as R minus JXC, R minus JXC. Please take note of that, R minus JXC, and all this correction you should implement it in your note. So that is that about that. So let's move on and see maybe some examples. So like we did in the past, if you look at this, if you have the impedance as 9 minus J14, it means that the 9 is for the resistance and XC is 14 ohms. XC is 14 ohms. So you can also express it in the polar form by invoking these formulas. That is, Z is the modulus of Z at an angle of phi, and the modulus of Z is square root of R squared plus JXC squared, and phi is arctan XC over R, arctan XC over R. So let's look at that of RLC series circuits. So I said in an AC circuit containing resistance R, inductance L, and capacitance C in series, the applied voltage V is the phasor sum of VR, VL, and VC as shown in the phasor diagram of figure 8B, where the condition VL is greater than VC is shown. So the phasor diagram may be superimposed on the Argand diagram as shown in figure 8C, where it may be seen that in complex form, the supply voltage V is given as VR plus J into VL minus VC. VL minus VC. So from the voltage triangle, the impedance triangle is derived, and superimposing this on the Argand diagram gives us this complex form of Z. That is, Z is equal to R plus J into XL minus XC, or Z is equal to the modulus of Z at an angle of phi. So these are an example. So determine the values of the resistance and series connected inductance or capacitance for each of the following impedances: A 12 plus J5, B minus J40, C 30 at an angle of 60, D 2.2 times 10 to the power 6 at an angle of 30 degrees. Assume for each a frequency of 50 hertz. A frequency of 50 hertz. So what do we do? So first thing is that we are going to look for, we have in the previous slides, we have been able to establish that for an inductive circuit, Z is equal to R plus JXL. Z is equal to R plus JXL. So that is, it means that our Z is equal to 12 for A, for this A, for the A here, A part of the question. Z is equal to 12 plus J5. So it means that 12 ohms represents what? The inductance, the resistance, sorry, it represents the resistance. And why the 5 ohms in series is inductive reactance, And we know that our reactance XL is what? 2 pi FL. It's 2 pi FL. So inductance L, when you make it subject of the formula, you have XL over 2 pi F. XL over 2 pi F. And we have been able to establish that our XL is 5. So we are assuming that our frequency F is 50. So you put them in the equation. So it will be 5 over 2 pi F times 50. And when you divide that, you are going to have what? 0.0159 Henry. Or simply put, 15.9 millihenry. So thus, an impedance 12.J5 ohms represents a resistance of what? 12 ohms in series with an inductance of what? 15.9 millihenry. So if you look at this, the B part, obviously you can see a negative J there, negative J. So when you see negative, automatically you know is a what? The capacitance. Is a capacitance. And that means that Z, it doesn't contain a resistance, a purely capacitive impedance. So it's going to be minus JX because the R will be 0. So it's minus JX. So it means that Z is what? Minus J40. So when you, and we know that XC is what? 1 over 2 pi FC. So when you make C the subject of the formula, you have 1 over 2 pi FC. So 1 over 2 pi XC. So when you put in the formula, the values of frequency, which is equal to 50, and XC, which is equal to what? 40, you are going to have 79.6 microfarad. So that means what we have in that circuit will be what? 79.6 microfarad. So for the C part of the question, you can see that based on this, Z is equal to 30 at an angle of 60 degrees. So it will now be equals to what? When you do it, when you do the trigonometric ratio, it will be 30 into what? Or 60 plus J sine 60. And when you do that, it's what? 15 plus J 25.98. 25.98. So what happens is that you make it you know that we want to find the help, and the help, because it is positive J 25.98. So automatically we know that it's going to be inductance. So XL is 2 pi FL, and here is what? XL over 2 pi F. So that is 25.98 over 2 pi times 50. So it's going to give you what? 82.7 millihenry. And so the D part of the question is what we want to do next. So now, what do we say? Look at this, give us 2.20 times 10 raised to the power 6 at an angle of minus 30. So like we did for the other one, it's going to be what? There's minus 30 there, so you must take note of the minus 30. So it's going to be 2.20 times 10 raised to the power 6, open bracket, cos minus 30 plus J sine minus 30. This which is equal to 1.905 times 10 raised to the power 6 minus j 1.10 times 10 raised to the power 6. So you can see that when you simplify, our z is 2.20 times 10 raised to the power 6 at an angle of minus 30. So it's going to give us 1.905 times 10 raised to the power 6 minus j 1.10 times 10 raised to the power 6 ohms. So what does that represent? It means that the resistance is what? 1.905 times 10 raised to the power 6 ohms. Or you can say 1.905 mega ohms. And we have a capacitance or a capacitive reactance of 1.10 times 10 raised to the power 6. So when you solve, you want to solve for the C. C is what? 1 over 2 pi fc. So when you put in the values, you are going to get 2.894 times 10 raised to the power minus 9, or 2.894 nanofarad. So you can lay your hands on it. I advise you that you still practice it and see what you are going to get. So if you have any question, you can let me know. So thank you very much.